I'm going to share a screen because this thing just came through from the president. It has to do with the coronavirus. Let's see, where am I? Recording, yes, we're recording. Pardon me for a second. There, should take care of that. Okay, share screen. And I'm going to share, which one? Where is it? I think it's underneath this one. Window. Yeah, here it is. Okay. So I'm going to put this full screen so everybody can see it. View. Here it is. Full screen. There we go. I assume everybody can see it. This is a flow chart that was developed by our COVID-19 response team. And one side is a flow chart for students, and the other side is a flow chart for employees. So I'm not sure if you're going to get one of these in email, but what I can do is post it in Blackboard so that you'll have access to this independent of any other contact that's made. So what does it mean? Well, it has to do with reporting requirements for the school. We have to report back to the health department on a regular basis, I think weekly. And we have to keep track of any exposures and development of symptoms and positive tests for the COVID virus. And so here's what we do. If one of my students reports an illness or an exposure or even a possible exposure, then you do two things. Go to the website, and this link will have a form that you need to fill out and submit to, I'm sure the form says where you're supposed to submit it. If all else fails, you can send it to me. Now this next part, if the student becomes ill while on campus, since we're not on campus, then I think we have a certain amount of latitude in how we respond. But if you're showing symptoms or you test positive, you still need to go to this site and fill out that form for the sake of the school's reporting requirements. But if you notify me of it, then I have to report it also. And then you'll be contacted once you report the occurrence. You'll be contacted by the Director of Student Success or the Dean and discuss the situation with you, and past that, it's out of my hands. Now, I have to do something similar. You know, if I show symptoms or I have experienced an exposure, then I go through my supervisor, and you don't have to worry about that one. But now you've been notified, and I'll make this document available in Blackboard. I'll just put a link on the left-hand panel, so when you first pop up in the 101 and 103, then there'll be a link on the side, same place that you find your Zoom link. So you won't have to go hunting for it. It'll be right there. Okay, so any questions before we get started with the with thermochemistry review? I might want to say a couple of words. Let me see about upcoming midterm grades have to be reported a week from yesterday. So on the 19th, that is next Monday, by the close of business, I have to report grades. And I was just looking at the syllabus to see what's what's due by that time. And it looks like the only thing that's due is the exam for the chapter we're covering today. That's for the Chem 101. And then for the labs, where is it? Here we go. The labs, the way, following my tradition and stated policy, Boyle's Law was, we would have done it on October 1st in face-to-face. So that means it's due on the 15th, which is day after tomorrow, the report for Boyle's Law. But the one on the 15th is not due till after the midterm grades are due. So you don't have to worry about the calorimetry lab until after midterms. But the Boyle's Law needs to be in my possession by the 15th. And if you get it to me by the 15th, then I'll have time enough to grade it. If it comes in late, then I may not have time to grade it before I have to turn the grades in. And if that's the case, a 0 will show up, but as soon as I get it graded, that 0 will disappear. It'll be replaced with a larger number grade, I hope. Okay, any questions before we get started? I'm going to get this thing out of my way. It's just hanging way too far over. Now I'm going to try something different this time. Instead of just referencing the review document and the numbers, you'll have a split screen, I hope. You've got me on half the screen and you got the shared screen on the other half. So it should be big enough that you can see what's going on my side of the screen where I'm writing on the board. So I'm going to go, let's see, I'm in full screen now, so I need to come back and close that one. And then, let's see, stop share. We're still sharing, so I should be able to put this one up in full screen. There it is. So what do? I assume everybody sees exam 4 review document. This is the key that goes with the review document. Is there anybody that can't see that? You don't have to say anything. If you can see it, then silence is golden. If you can't see it, then speak up. Then that means something else is going on. But I'm going to reference this, and like I said, you should have split screen on so you can see not just a little thumbnail of me in the upper hand corner. You want to see me on half the screen, only because then you can see what I'm writing. As if it's just a thumbnail, it's too small to, the resolution is too small. Okay, so let's get rolling here. Get my marker out. And I've got some picked out like I did last time. And I'm just going to run down through them, unless, of course, if you have an issue that pops up in the middle of, just interrupt me and we'll cover your problem before the end of the class, so we'll be sure and get everybody's concerns wiped out. If not, then I'll go ahead with number 1. Let's see. I'm thinking that we've got some others showing up. I don't want to miss anybody. So let me take just long enough to check my roster. Let's see, I need to stretch it a little bit. There we go. Okay, not here. Justice is here. I thought so. There we go.
Yeah, sorry about that.
That's okay. I don't want to leave anybody out, especially since you get credit for being here. Okay. So number 1 says, a gas absorbs 0 joules of heat. That means there's no heat transfer. So let's put it in a cylinder with a piston. So there's our gas, and there's no heat transfer. Q equals 0. All right. But the gas performs 30.7 joules of work. So the work is 30.7 joules, but the sign is very important. If a gas is performing work on its surroundings, by convention, what should the sign be? It should be negative, right? If we're adding something to the system, then it's positive. If something is leaving the system or the system is doing work on the surroundings, it's always negative. So that needs a negative sign. Now what's the question? The change in internal energy. Right? Remember our formula. The change in internal energy is equal to the heat transfer plus any work that's done. So with Q equal to 0 and W equal to minus 30.7, then delta E has to be 30.7, minus 30.7. Start off with the easy ones. So that's why the answer is D. I'll still write the number up here. All right. So let's make room for number 2. What is the kinetic energy of 1.56 kilogram object moving at 94 kilometers per hour? Okay, kinetic energy. So the question is, what's the kinetic energy? How do you calculate kinetic energy? Equals 1/2 mv squared, right? But for this to be joules, the units of mass has to be kilograms, and the units of velocity has to be meters per second, right? So let's see, what do we have so far? We have mass is equal to 1.56 kilograms. And the velocity equals 94 kilometers per hour. All right. Can we plug those numbers into that formula and get the right answer? No. Kilograms is fine. Velocity is not. We need to convert this to meters per second, right? So you've got kilometers, which has to be converted. You have hours that has to be converted. So based on our experience with dimensional analysis, you convert 1 unit at a time. So a conversion factor for converting, let's do the kilometers first. All right, got to cancel kilometers, that's why it's on the bottom. So how many kilometers, we can go straight from kilometers to meters. So how many meters in a kilometer? 10 to the third. Right. That one's done. How about hours? Well, if you don't know, you could convert hours to minutes and then minutes to seconds. But if you've done it as often as I have, you know that the conversion factor, hours on top to cancel, right? Seconds on the bottom, and the conversion is 3,600. Right, because 60 seconds in a minute and 60 minutes in an hour, 60 times 60 is 3,600. So there we've got kilometers per second. Now what you can do is you can either go through and find out what it is, meters per second, right? And then plug it into the formula. Or you can say, to save time, Now that you've got this, you can say, that's your velocity. Square it, 1.56 kilograms, and 1/2 times that. And there you go. And you can do all of that work in your calculator in one shot, whichever you're more comfortable with. So let's see if it works this way. So I'm going to do this part first because it has to be squared. So 94 kilometers per hour times 1,000 and divided by 3,600. And then square it. Let's see, where's my square? Here it is. Okay. Then times 1.56 and divided by 2. So I get 531.796. Joules. Now let's see, we've got 3 significant figures here. Those don't count, right? Because those are all exact. All conversion factors are exact numbers. So you only have to pay attention to the original. So that one has 3, that one has 3. So we need 3 down here, right? 532 joules. Let's see, do we have an answer for that? It's in kilojoules, naturally. So if that's joules, what's kilojoules?
5,000. You divide that by 1,000.
Divided by 1,000, yes. So it'd be 0.532 kilojoules. And of course, they're in scientific notation. Just take a look at your answers. So that would be 5.32 times 10 to the minus 1 kilojoules. Now we can find our answer, and it's A. Now you all know this document that I'm sharing is in Blackboard. All right, so you can copy it down if you want, but you got backup there in Blackboard. All right. So that was 2. That also illustrates the fact that real world problems are rarely one step. You usually got more than one step that you have to deal with in the real world. Okay, 3. Which of the following statements correctly describes the signs of Q and W for the following exothermic process at pressure equals 1 atmosphere and temperature equals 370 K? For water going from gas to liquid. So we're looking at the signs. So let's draw a picture. I like pictures. So if we've got water going from a gas to a liquid, and there's one assumption that I think we have to make in here. And it has to do with the fact that the pressure is 1 atmosphere and it stays 1 atmosphere. So the only way to do that is to put our gas in here and let it go to a liquid in there. And then there's 1 atmosphere pressure on it. Okay, and the temperature is 370 degrees, which is and it's an exothermic process. So in order for it to remain 370 degrees, and it's exothermic, if we're producing heat in here, if we're producing any heat in there, then in order for it to stay 370 degrees K, some heat has to leave, doesn't it? In order for us to maintain the temperature of 370 K. So if the temperature has to be constant, then all the heat that we produce in here has to leave enough of it to maintain that temperature. Okay, so what happens to Q? What's the sign on Q? Well, if Q is leaving the system, it's negative, right? So, and that's characteristic of all exothermic processes. Q is negative. So we got that one taken care of. Now how about W? Right. So as the gas condenses under this pressure, that piston's going to drop. And with that being known, a force is applied over a distance which is applied to the system. So work is being done on the system. You can think of it in terms of which way is the gas going? Is it expanding or contracting? If it's expanding, you can usually say the system's doing work on the surroundings. It's kind of like a piston in a car engine. When here's the piston, here's the cylinder head, here's the piston up here. Spark hits it and it goes bam, like that. The gas expands, and it's that's a bad example. No, it's a good example. Now that I come to think of it, it's just we have to turn it over like this, turn it upside down. So as the gas expands, it's doing work on its surroundings. And if a gas contracts, then work is being done on the system. So that would happen during the compression phase of the automobile engine operating. So I said all that. If it's contracting, then work is being done on the system, which means W is what? Positive. So let's see. The answer given is C, which is Q is negative, W is positive. Okay. Let's see, am I still on screen? There, I better pull it back just a little bit. It's kind of walking on me. Okay, yeah, I got 4. Let's do 4. For a particular process, Q is 20 kilojoules. This is 4. Q is 20 kilojoules. And W is 15 kilojoules. And those, because they don't have a negative sign in front of them, we have to assume they're positive. Okay? Which of the following statements is true? Well, let's see. If we've got a system and heat is positive, that means it's endothermic. Q is positive to the tune of 20 kilojoules, and W is positive 15. So work is also being done on the system. Okay. So now we have our picture. We know which way everything's moving. So actually, the internal energy of this system is going up, way up. Heat flows from the system to the surroundings. Heat flows from the system to the surroundings, false. A's out. The system does work on the surroundings. No, surroundings are doing work on the system. B's false. Delta E equals 35 kilojoules. Delta E equals Q plus W equals 20 plus 15 equals 35 kilojoules. So C is true. D says all of the above, false. None of the above, false for E. So C is your answer. So the moral of that story is, if you reason it out first, what information are you given, and draw yourself a picture. So you get a visual representation of what's happening. Then when you look at the choices that you have, the selection is quick and easy. All right, let's see. I got this one selected too. 5. All right, so we've got to find out which of the statements is correct. We look at our choices. We have a D that says all the statements are true. E says all the statements are false. So if we find one true and one false, then D and E are both out. So we just have to take them one at a time and see if A is one and B is a different one, like what's true or false. Then we know that D and E is out, and we can go. That means that only one of them is true. So if you do A and B and you find one of them is true, then you stop. But if both of them are false, then you got to go to C. Check it out. So let's see what they say. The internal energy of a system increases when more work is done by the system than heat was flowing out of the system. We need a picture. We need a picture. Definitely need a picture for this one. Right? So we've got Q and W, and they can be going one of the other directions. We're going to put arrowheads on there depending on what the statement is. So the internal energy, okay, that's the first part. Let's go to the end and work our way backwards. Let's see. More work is done by the system. Work done by the system, which means work done on the surroundings. Heat was flowing out of the system. So what we're saying is these are both negative. And well, we can stop there. If work is being done on the surroundings, or work is being done on the surroundings and heat's flowing out, the internal energy has to decrease. So A is false. The internal energy cannot increase, which is the first condition of A, right? So A is false. How about B? The internal energy of the system decreases when work is done on the system and heat is flowing into the system. It's just the opposite. We'll go the other direction. And in that case, it says the internal energy decreases. False. It has to go up. If work is being done on the system, if heat's flowing in, internal energy has to increase. A and B are both false. So we need to go to C because E says all the statements are false. Right? So if we find that C is false, then E is the answer. But if C is true, we stop there. So let's see, what does C say? The system does work on the surroundings. All right. System does work. System does work on the surroundings. Okay. And system when an ideal gas expands against a constant external pressure. If the gas is expanding, against a constant external pressure, does work on the surrounding. Oh, okay. It doesn't say anything about heat, does it? It just says something about work. When the system does work on the surroundings, the system does work on the surroundings when it expands against a constant pressure. And that goes back to number 4, 3 or 4, where I said, if a gas expands, you can generally say it's doing work on the surroundings. So, C is true. All right, that's 5. And I need to pick up the pace. As usual. Let me see, I had 7 marked. Let me see if it's worth tackling. 7, 1 mole of an ideal gas is. How much work is performed on the surroundings? Okay, let's do 7. I think there's some value in that one. All right, so 7 says 1 mole of an ideal gas, 1 mole of an ideal gas is expanded from a volume of 1 liter to 8.93 liters. So initial volume is 1 liter, and final volume is 8.93 liters. Okay, I'm just putting all our information up here so I can see it better. And it's expanding against a constant pressure of 1 atmosphere. Okay. How much work is performed on the surroundings? And our answers are in joules, are they not? Okay. So, what's the formula for work in an expanding gas? If the pressure is constant, then of course we know that delta H and Q are equal, but that's not important right now. What we want is the formula. Work equals minus P delta V. Right? And we stick that minus in there in order to make the work sign come out correctly for our convention. So a constant pressure of 1 atmosphere and a change in volume. So a change in volume is always final minus initial. All right? So W equals minus 1 atmosphere times final minus initial, and that's liters. So what do we have? That's a positive 7.93, is it not? Times a 1, so it's a 7.93 minus sign, 7.93 liter atmospheres. All right. But your choices are not in liter atmospheres. Your choices are in joules. So we need a unit conversion. So the unit conversion is given for you right there. 1 liter atmosphere equals 101.3 joules. So this one needs to be converted I think 101.3, didn't I say? Where am I? Yeah, 101.3 joules for a liter atmosphere. For 1 liter atmosphere. So this is in the numerator. This is in the denominator. We'll cancel. So we just need 7.93. Change sign. And 101.3. Made a mistake. Enter. Okay. 101.3 times. And our answers are in joules. So I get 803, negative 803 joules. rounded off to 3. Okay. And it looks like that's B. Okay. That's number 7. All right. Now let's see. I've got 9 marked. Nine might be worth doing also. If for no other reason, to test to see if I can remember how to do it. So a fuel air mixture is placed in a cylinder fitted with a piston. And this would have to be in some sort of protective container, like a bomb calorimeter, with a moving piston, of course, because there's going to be a lot of energy released. The original volume is 0.310 liters. So the original volume equals 0.310 liters. And the question is, what's the final volume? Right? We don't know that yet. Okay, we're going to ignite the mixture, and we get 935 joules of energy released. So let's read the rest of it. We've got that much energy released, so it's exothermic. To what volume will the gas expand against a constant pressure? Okay, so the pressure is constant. That means, and we're stipulating that all of the energy released goes into moving the piston. It's an isolated system, right? None of the energy escapes to the surroundings. So work is actually what we're talking about, 935 joules worth. And at a constant pressure of 635 millimeters. Okay, there's all of our information. How are we going to solve the problem? We got to find the final volume. And we've got work given to us, we've got pressure and volume. So the formula that ought to come to mind is the one we were just working with. W equals minus P delta V. So we have to have units that are compatible with liter atmospheres. Why? Because we can't use joules. This expression is not in joules. So we need to convert this to liter atmospheres. And oh, it doesn't give you that, does it? You'd have to look that up in useful information. I know it's in there. Or if you see another problem that's got it in it, 101.3 joules per liter atmosphere. Right. So whatever that value happens to be, let's go ahead and calculate it. 935, 101.3. So that's 9.23. Okay. Pressure needs to be in atmospheres. .760 millimeters of mercury is 1 atmosphere. So 635 and divide by 760, we get 0.8355. 0.8355 atmospheres. Now we can use that formula, right? So the work done is actually 9.23 . This needs to be a sign also, doesn't it? 935 joules of energy is released. So for the piston to do work on its surroundings, that has to be negative. And then negative pressure, 0.8355 atmospheres. And then final volume minus initial is 0.310. Okay, so now you just solve it for V. And in the interest of time, I'm going to take the answers, the keys word for it. It says that the answer to that one is 11.4 liters. You can verify it. Let's see, does it look reasonable? Well, we would expect it to be larger than the original, right? So it's got that good. This is roughly 1, right? So if we say that's 1, then that means this one minus that one. Actually, it's minus this one plus that one. So this one becomes added to that one. And yeah, it's in the ballpark. Right. It's in the neighborhood of 10. All right, so that's close enough to say, all right, we probably did it right. Okay, let's move on to something else. Some of these problems take a little time to work out. Let's see. Well, we could look at 14 through 17. That shouldn't take too long. Let's go down 1, 2. There we go. So for 14 to 17, we're working with a system that has a 1 liter bulb of gas. So it's 1 liter volume. And the reason I'm leaving that open is because there's going to be a valve. And it's connected to another with a valve to another. Is that one 1 liter also? It doesn't say. It's evacuated. So this is a vacuum until you open that valve. And of course, when you open the valve, there's going to be, that's going to rush in here. It's not going to all go over there, right? It's going to, some will go over there until you get equal pressure. So when this process occurs, what can we say about these 14 through 17? So 14 is, let's see, QW delta E, QW delta E, and delta H. Okay. What can we say about Q? This is all at standard temperature and pressure. What that implies is that it's an isolated system. It's held at standard temperature and pressure. So if there's no change in temperature, there can't be any change in heat, because heat only transfers when there's a difference in temperature. Right? So this one is 0. What about work? Is there any work done? The gas moved, but there was no force applied. Right? So if there's no force, there's no work. There's a change in volume, of course, but you got to have both, force and distance, to have work. So since there's no force applied against anything, that one's also zero. Okay, how about delta E? Delta E is the sum of Q and W. That's zero. How about the enthalpy, the thermodynamic heat potential for this reaction? Well, we're saying that the pressure is constant, but I don't know how you can manage the pressure to be constant. If you got 1 liter here and it expands into another, so the pressure has to be different. Temperature, yeah, you can account for that, but the pressure can't be the same, not if you're expanding a gas into a vacuum. The pressure is going to go down. In fact, we proved that in one of the problems we worked in the last chapter, right, where we expanded a gas into a vacuum. No, we expanded a gas at one pressure into another bulb at a different pressure, and we used Dalton's law of partial pressures by theorizing one movement into a vacuum and the other one movement into a vacuum, and then we could add the resultant of each one together to get the final. But for each step moving into a vacuum, the pressure is not the same, right? You do get, so we can't just automatically say that Q is equal to delta H, but we don't have any choice. We can't say what delta H is. What are our choices? Greater than 0, equal to 0, less than 0. More information is needed. In this case, we have to choose the best answer. And since there's no difference in temperature, the pressure doesn't matter. That's my logic. Let me say that again. Since there's no change in temperature, then we know Q is 0. But since there's no change in temperature, the enthalpy doesn't change either, regardless of what the pressure is. Because any transfer of heat, whether it's actual or theoretical, thermodynamic, has to be accompanied with a change in temperature. That's the only way that heat will move. So that's why I'm saying that delta H is 0 also. So all of these are 0. Did I lose anybody in that one? Let's go ahead and do 18 while we're here. For these terms, energy, work, enthalpy, and heat. Energy, work, enthalpy, and Q, heat. Which ones are state functions, or how many of them are state functions? We might as well say which are path functions too. Work and Q are path. And E and H are state. If all else fails, memorize it. Then you can use it to do something. Okay. Let's see. Let's look at 23. 23 will go quickly. So 23, consider the reaction C2H5OH is ethanol. That's the drinking kind of alcohol. We're going to burn it. So it's a combustion, ethanol with oxygen, yields carbon dioxide and water. So that's typical for complete combustion of any organic compound like that. And then the delta H is minus 1.37 times 10 to the third kilojoules, right? So that's a lot of energy. Now that's kilojoules for that reaction, right? So what does that mean? That means that for this particular reaction, oh, 23, excuse me. Here, pardon me. For this reaction here, it has a negative enthalpy. The thermodynamic potential is the release, exothermic, negative value, exothermic release of, let's see, let's move the decimal place, 1,370,000 joules. Okay, it's a lot of energy. So, of these propositions, which of them are true? Roman numeral 1, the reaction is endothermic. False. Delta H is positive for endothermics. Endothermic means heat is moving, would move into the system. We're defining our system as everything here that reacts. Both reactants and products are in the system. So 1 is false. 2, the reaction is exothermic. That's true. Delta H is a negative value. It's exothermic. How about 3? The enthalpy term would be different if the water formed was gaseous. Just take this as a rule. The states of your reactants and products matter, because changing from one phase to another requires heat in or heat out, whichever the case may be. So if the phases are different, the enthalpy is going to be different. So 3 is also true. Okay, so 2 and 3 are true. That means E is the answer to 23. Okay, so here's a calorimetry problem, number 24. It's a simple one, so we're going to start simple. All right, what are we given? Well, the question is, how much heat is required? All right, there's the tricky wording here. When it says how much heat is required to raise the temperature of a sample of iron from such and such to such and such. So that means heat is we have to add heat to the iron. How much heat is required? If it had said how much heat is evolved when blah, 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 that means heat will be leaving the system. So the wording is important here. That's what's devious about word problems. Okay. So fortunately, though, all the answers are positive, right? So really all you have to worry about is the number, the size of the value. Okay, so how do we calculate this quantity? How much heat is required? Remember the definition of specific heat. It's the heat that's required or evolved is equal to the specific heat value for the substance times how much of it is there, mass, in this case mass, and then a change in temperature. Okay, so there's your operative, formula. And we're looking for this one. So we need terms for these. So what's the specific heat of iron? 0.450. Which is joules per gram degree centigrade. How much mass do we have? 5.75 gram sample of iron. 5.75 gram sample. Okay, and check your units as you go, right? Grams, cancel grams, we're good there. So we need a change in temperature. So what does it say? The temperature is going from 25 to 79.8. The final temperature is 79.8, which means it goes first. Minus the initial temperature, 25 degrees. So grams cancels, degrees cancel. And we're left with joules, which is the correct units of measure. So just resolve that expression, and you should end up with 142 joules. Okay, and the fact that it's a positive value after doing this calculation confirms the fact that heat was required. The system, which is the chunk of iron, absorbed that much heat in order to get its temperature to go from 25 to 79.8 degrees. Okay, we're coming up on 1:30. So I need to find a problem that incorporates let's see. I'm going to look at my handwritten solutions. That's easier to find the one I want. And we're not going to have time to do all the ones that I'd like, but let's at least do a calorimetry problem, and maybe we can squeeze in a Hess's law. I'd like to get a Hess's law, so let's do the calorimetry quick. Let's see, where's a calorimetry problem? Okay, that's a good one. There's another one. Let's see what 40 looks like. Back up. There we go. Okay. That's a good one. Number 40. All right. So I'll just read it off of that. We've got 4.4 gram sample of Colorado oil shale, which just means there's a lot of mineral in there, but there's also something that's combustible. So we're going to burn it in a bomb calorimeter. 4.4 grams is the sample size. 4.4 grams. Okay. The temperature of the calorimeter increases by 5 degrees. So it doesn't tell you it goes from this to this. It just says delta T is 5 degrees. Okay, that's fine. The calorimeter contains 1 kilogram of water. So this is the mass of the shale. Mass of the water equals 1 kilogram, which is equal to 1,000 grams. I know I'm going to need grams because the specific heat is in grams. The heat capacity of the empty calorimeter is 0.1 kilojoules per degree C. So big C, which is the calorimeter constant, is 0.10 kilojoules per degree C. Or that's equal to 100 joules per degree C. Okay, that's everything we're given. Now the question is, how much heat is released per gram of oil shale? So what's the Q value for the shale? All right, the setup of this problem is the key. What things are going on and what kind of system do we have? The bomb calorimeter is an isolated system, which means everything that happens in the calorimeter stays in the calorimeter, which means the total is always equal to 0. So what heat components do we have adding up in here? Well, we have a Q for the shale, right? That's how much heat is being evolved by the shale. We have the Q change for the water. And we have the Q for the calorimeter. We have those three terms. Okay. I think I'm going to run out of time before I get a chance to do Hess's law. So I'm just going to keep going. My office hours aren't until 2 o'clock, and I can run over a little bit. So we got to get Hess's law in there, definitely. So let's go ahead and finish this one. So what are the terms? How do you expand the Q for shale, the Q for water, and the Q for the calorimeter? Well, the Q for shale is a single term. It's just joules, right? So that's going to be our unknown. And that's typically the way it is. So this is our unknown. That's our question. So how about water? Well, the water is going to be SM delta T. How about the calorimeter? Well, the calorimeter combines specific heat and mass in one term. That's this one. So this one is only C times delta T. And that's always the case for calorimeters. Why do we do that? Because the actual specific heat for the calorimeter can't be determined. You have to determine this value for the calorimeter and only that calorimeter construction. If you change anything about the calorimeter, then the C changes. So this is peculiar to each calorimeter. That's because we've got so many components in there in the calorimeter, you can't tell what the S value is. It's impossible. Some of them are like the ones that I showed you in the lecture. They're styrofoam cups, and they're the lids, and they're the thermometer, and some of them have stirrers in them. So if you change the thermometer, you change the C value. So that's why we have to combine these two into that term. But we're given that term in this case. We would have determined it experimentally, and that's what you do in the lab, the calorimetry lab. I'll show you how to do that in the calorimeter lab. Okay, so we're solving for this one, and we need what is SM delta T, right? So let's see. Let's pull this out. So 0 equals Q for the shale plus water is 4.18, is it not? 4.184. 4.184. I'm going to leave the units out because they take up too much room. Times the mass of the water, which is a kilogram, 1,000 grams, right? Because this is in terms of grams. And then the delta T is 5 degrees C. Right? So there's our water. How about the calorimeter? Well, let's see. The value that was given was 100 joules per degree C, right? We're going to keep it joules because this term is going to be joules, right? This value comes out in joules, so we need to use the joule equivalent here. I just said I wasn't going to do that, but I wrote it in anyway. And then the change of temperature is 5 degrees. So the degrees cancel here. It leaves us with joules. The degrees, the mass cancel, leaves us with joules. And there we go. So 0 equals Q of shale plus 5,000 times 4.184. Okay, that's 2.092 times 10 to the fourth. And then 5 times 100 is 5,000, right? No, 500, excuse me. 500 joules. So this one plus this one plus that one is equal to 0. So if we leave this one here and pull that one over there, it's a negative value, right? So what's this one plus that one? So let me just add 500. And then this one becomes negative on the other side. So I'm going to leave this over here just so I don't confuse everybody. This stays here. This term moves over here to be negative at 2.14. Let's see. Well, we just keep all 4 of them. Joules. All right, so that's how many joules for the reaction. But the question is, how many joules per gram or kilojoules per gram? So how many kilojoules is this? Let's go ahead and convert it. We're going to take 3 of those powers and turn it into a kilo. So it's minus 2.142 times 10 to the first kilojoules. And how many grams are there? 4.4, right? So we divide that by 4.4 grams. And I get 4.87 kilojoules per gram of shale. And let's see. The nearest one is D, 4.9. And why did they do? Oh, because there are only 2 here, 2 significant figures, so that should be 4.9. Yep. Okay. Now, I got 4 minutes to do Hess's law. So let me see if I can find one that's doable in a short period of time and still gives you some exercise our brain cells. Let's see, Hess's law. That one's pretty involved. So that one. I don't think there's going to be one that's really short. Maybe this one will work. Number 70. Okay, 70, using the information below, calculate. Oh, that we're doing heats of formation there. That might be a little more than we should tackle at one time. Let's go. Okay. 87. I'll just keep talking even after the time's out, and we'll finish this one. So, 87 is Hess's law. The solution to it is Hess's law. So let me erase some of this. Move this one over, this one over. Go. '87. Okay. So 87 says, with the following data in that table, you have these component reactions that you can use to construct the net reaction at the bottom. So we want to find what's the change in enthalpy for the following equation. Calcium carbide, that's CaC2, which is stuff that miners used to put in their lamps when they used carbide lamps. They put a bunch of these crystals in their lamp, and then they open their water bottle and squirt some water in there, and the reaction would be spontaneous. It would produce calcium hydroxide and C2H2. C2H2 is acetylene, and that's what would burn in the miner's lamp until they hit a seam of coal dust or methane pocket, and then the whole place would blow up. That's why they went to electric lamps that were properly insulated. So one of the reasons that mining was very dangerous in the good old days. Anyway, 87. So our final reaction is calcium carbide, solid, plus water, liquid, yields calcium hydroxide, aqueous, calcium hydroxide, aqueous, plus acetylene gas. Okay, so there's our target reaction. All right, what we need to do is account for each one of these components in the reaction in the available reactions. So if we just go down the line and say there's calcium, there's carbon, there's calcium carbide, CaC2, right? So we could use that one. Are there any others with calcium carbide in them? No, we're stuck. We have to use that one. So let's go ahead and put that one up there. Calcium carbide is on this side, but the calcium carbide reaction in our table is on the wrong side. So we have to switch it. And this will be calcium solid plus carbon or graphite, two of them. And now the delta H for this reaction is positive because we flip the reaction. So it's plus 62.8. Is that kilojoules? Yeah, kilojoules. Positive. Okay, so now we got these two. Got those covered. This is our target. This is the component. How about the others? Water. You have anything with water in it? Yep, there's water. Okay, so water in this one is on the correct side, so we can use it as is, and there's a right number of waters. There's only one water on that reaction. So calcium oxide plus water, and it's the correct phase, right? It has to be liquid water, yields calcium hydroxide. Aqueous. Okay? And we can use the value that's given there as is because we did not change the reaction at all. Minus 653.1. Okay? So that means we got this one there, and we got the calcium hydroxide. Okay? So what else do we need? We need acetylene. So where's the acetylene? There's acetylene. That the only place? It's in the next to the last equation, acetylene. So acetylene is on the wrong side here. It needs to be on the other side. So we have to flip the reaction, and there's only one acetylene here, and there's only one acetylene here, so we only have to invert the reaction. So now we're going to have 2 carbon dioxide and 1 water. Yields acetylene, gas, and 5 oxygens, 5 halves oxygens. Okay, so that one and that one. And we have to change the sign, plus 1300 kilojoules. Okay, so at this point, we've taken care of these, but we've added some things too. Like we added calcium, we added carbon, we added calcium oxide, we added a water, right? We only need one, but we added another one. And we added oxygen. Right? So these are taken care of here. Now we added carbon dioxide. Let me put a box around those. Right? That one, that one, that one, that one are accounted for. And in the process, we added these extras. So now we have to get rid of those extras. So we've used calcium carbide. We've used the first one, calcium oxide. We've used the third one, and we've used the fourth one. So we've got 2, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. We got 5 and 2. 5 and 2 left over. So the second one is calcium plus oxygen yields calcium oxide. So which side is calcium on? On the right-hand side, and calcium oxide's on the left. So calcium oxide is on the left. Let's see. Which one am I looking at? Second one, number 2. So with number 2, the given formula is calcium on the left, calcium oxide on the right. But we need calcium oxide on this side and calcium on the right. Right, so that one has to be flipped. So that's calcium oxide on this side. Oh, excuse me. No, we don't. Why not? Because we're trying to cancel them, right? So if we want to cancel this one, calcium oxide needs to be on the right. And it already is. So we can write it as is. Calcium plus 1/2 oxygen gas. Is that gas? Yeah, this one's gas too. Yields calcium oxide, solid. Okay? And how much energy is that one? Minus 635.5. Minus 635.5 kilojoules. Okay, so what does that do? Well, let's see. There's calcium. Calcium's gone. Calcium oxide. Calcium oxide's gone. 1/2 of an oxygen. 1/2 of an oxygen from 5/2 of an oxygen yields 4/2 of an oxygen, or 2 oxygens left over. So we got 2 whole ones left there. Okay, so now we still got that one. We've still got water, carbon dioxide, carbon, and oxygen. So 1, 2, 3, 4, 5. So if 5 doesn't do it for us, then we're in trouble. Carbon dioxide, let's look at the last one, number 5. Carbon dioxide needs to be on that side, but we need 2 of them. So the direction is correct, but the number is not. So we need 2 carbons and 2 oxygens yields 2 CO2s, right? Right, 2 CO2s. So now what do we do with the enthalpy? We have to double it. So minus 393.51 twice that is 787.02. Okay. 2 oxygens. Gone. 2 CO2s. Gone. And 2 carbons. Gone. Uh-oh. What happened to that water? Carbon dioxide and water. Calcium oxide and water. Okay, so how did I end up with an extra water? Did I not cancel one? All right, I made a mistake somehow. 87. Water. There. 1, 3, 1, 2, 3, 4 water. Yeah, there's something wrong with this picture. Oh, I know what it is. Anybody see the mistake? I wrote the original equation wrong. See, the devil is in the details. So we're good. There, that one. These all in the boxes are canceled. Now, all we have to do is add these up. And that will give us our our enthalpy for this reaction. That's a lot of trouble to go to, but there it is. Other problems like the next one, 88, that one is where you take the heats of formation for each. I think we can do that one pretty quick. All right, so 88 is an exercise. I'm gonna have to use a different color because that one's starting to give out on me. Our operative formula here is the delta H for the reaction is equal to the sum of the delta H's of formation for the products minus the sum of the delta H's of formation of the reactants. Okay, and each one of these is multiplied by the number of moles, which is the coefficient in the balanced equation. Right, so don't forget to do that. So for this example, we have P4O10, P4O10, and 6 waters, solid, liquid, yields H3PO4. Okay, so we just take 4 times the value of formation for H3PO4, which is minus 1279. So 4 times minus 1279 kilojoules, probably. Yeah, kilojoules is the product side. Then we subtract the reactant side. We have 1 P4O10, which is minus 3110. And then we have plus 6 times water, minus 286. Minus 286. There we go. This is a really simple one. So you just say 4 times that value. Don't forget the sign. And then this one is 6 times minus 286. And this one is minus 3110. Add those together. Change the sign. And then add them to that one. And I get 4775, which is wrong. What did I do wrong? I must have messed up the signs. Okay, in that case, let's do it this way. Minus 286. Oops. 286. See, do I have the right values? 286 for water. Yes. 6 times that. So that's minus 1760. And then this one is minus 3110. So we put those two together. We get minus 4826. Minus 4826. Minus that is plus. And then this one is 1279 is minus 5116, then plus that one. Minus 290. Okay? All right. There are a whole bunch of other problems in here that we could spend a lot of time on. But time is something we don't have much of. So I would suggest going through the ones that we didn't cover. If they're not exactly like the problems that we worked already, and see if you can do them. And if you get stumped with the answer or with the worked problems, it doesn't help you any, then come see me during office hours. Of course, office hours now start right now, but I'll have office hours tomorrow in the morning also. And we can iron out those problems. Okay, I'm going to stop the share. There we go. And that's all I have time for today.